Our new chapter here. By the way, we start to assign attendance from this class. Okay, later in every class we will assign attendance. If you didn't, okay, do it before you leave. Okay, so in previous two chapters, you'll learn more or less about statistics. Okay, so how we access data, how we describe data. Okay, so before we really talk about statistical inference, how we get some good conclusion or get some good guess about the population, the one we are interested in. Okay, we need to know how to correctly guess. So this requires to have a correct foundation for probability. Okay, so let me find my pen here. Okay. Okay, I guess for probability itself, you have learned more or less in your high school. So I guess today's class is more likely to let you know how to use English to say the terminology. Okay. But I think by the last 10 to 15 minutes, I will talk about something interesting. Okay, that's usually something you haven't learned uh, in your high school. Okay. So before defining the probability, we first need to define what is a random process. Okay, so we mentioned about random a lot of times. Okay, you are likely also learn what is a random. Um, so basically, to facilitate discussion, we define a random process as some process we don't really know which particular outcome would happen, but at least we know that what kind of outcome exists. Okay, so we know all possible outcomes. Maybe we have no unknown. Or in a simpler way, right? Even though we just only know like several possible outcomes, and for the remainder, we may have no idea, but we can cover them as other outcomes, right? Let's say maybe for the 60%, we know that there are A, B, and C three outcomes. The remaining 40%, other outcomes. That's also one way. Anyway, to make sure that we can correctly define the process, uh, we should make sure that we have some definition for each possible outcome. Okay, that's for any of the possible outcome. We don't really know at the end what which one will really comes out. Okay, so we have point calls, die rolls, different events. Okay, so point calls. Slide. Uh, yeah, okay. One, two, six, pages. So, we know what kind of outcome exists because we know comes out, but at least we can define the probability, like which one will likely to happen, okay, in what kind of level they will likely to happen. Okay, it's already defined as probability. So for a single event, okay, we formally call the one outcome, one particular outcome as events. So sometimes, okay, we sometimes use the events to cover more than one event, more than one outcome. Okay, that depends on your definition. Okay, so anyway, for specific events that covers one or more outcomes, okay, if we define it, if we call it A, event A, then we can always define the probability of event A to describe how possible, how likely that event will happen. Maybe use the notation PA here. So any PA is, it must satisfy the range which required to be between 0 to 1. Okay, so we define 1 as sure, we define 0 as impossible. So any possible events, any probably happen or probably not happen events should have its probability within the 0 to 1 range, as long as we go to 1 of possible. So I think this is kind of definition you have learned this in high school. Okay. Just something we want to mention here is what you really need to know about the colleague is two interpretation from two different trends or two different direction of statistical analysis. Okay, so the one side is called frequentist, or the other side called Bayesian. So the frequentist is like the most conventional like this. Okay, so what they believe is that the probability is basically the truth, the hidden truth of the universe. Okay, sometimes the truth is very easy to observe, like the coin toss, right? Each outcome will have a different probability. By using a simple logic, you know this one should be true. And some of the truth is not easily observable. Like if you construct a very complicated machine, how like if this machine is based on electronical engine, okay, how much power this engine can output, right? So you need to test, right? You need to have your analysis. But by the end, you need to make your experiment to see how it works in real world, right? So the frequentist interpretation is that any kind of probability is a hidden truth of this world. Right? It will exist somewhere. Although because of humanity's limitation, we may not be able to really observe probability for everything in our world, in our universe. But we can learn. We can try to find. Okay. So the way to find the probability, the way to get closer to the truth is to repeat the specific experiment for an infinite number of times. As long as we repeat it for more times, we are closer to the truth. Okay, so that means so here an implicit assumption is that although this one looks very common sense and looks very understandable, seems like an axiom, like we don't need to assume anything, but actually this argument has some assumption. Okay, the implicit assumption is that the probability is a fixed number. You toss this point is the probability for height must be 50%. Okay, maybe it's just if we don't practice, maybe we don't really know if this is 50%. Okay, so we practice it first, we realize this 50% do exist even if we don't see the coin. Okay, so this looks very good, right? And very reasonable, looks very confident. On the other hand, the Bayesian's interpretation is totally different. The Bayesian inference, they basically do not believe anything. Okay, they feel that there is no true probability in this world. Okay, probability, there is no fixed number for any probability. Okay, so even for coin toss, let me argue that, okay, it is because you are on the Earth. It is because you are assuming that you are having a fair coin. It is because of all the physical rules in our Earth, so that any coin toss will get exactly 50-50 probability. So if within the same universe you move to another planet, maybe so far away from the Earth, and there are different physical rules running that planet. Okay, and you force the same point, maybe because of the very complicated gravity rules, the result for every pattern should not be 50. Well, sounds really scientific, but well, it's hard to say that's impossible. Sounds a bit reasonable in some way, but well, who will think about that, right? So just from this way of thinking, if they define the probability as a subjective degree of belief. So all the probability is subjective. That means it's kind of depending on the humanity's opinion. So if there are two different people, they may have two different beliefs for the same events, and they will assign different probability for these events. So although the frequentist interpretation looks easier to accept, but for current society, I would say if you really think about the application of the statistical inference, you may aware that the Bayesian rules or the Bayesian interpretation is mostly well spread. Okay, the frequentist interpretation does not look that much because there are not much events that we can that we can identify clearly, right? So if we use some very easy events to establish the theory for probability like point for paralleling, if we really can easily to understand that those events have a certain probability for certain outcome. So, but what if we are talking about some more complicated events, like whether the stock market will rise or drop tomorrow? We know that almost everything in this world is connected. Maybe connected to the stock market, right? So the economic condition, market trading behaviors, or even, for example, the emotion of Donald J. Trump. Right, maybe tomorrow because we don't know what kind of things will happen in the spring. Maybe tomorrow he just find some new ideas to probably say, okay, this country, that country, you get 100% tariff. Right. This just happened within this year, right? So all everything, things we know, we don't know, it does happen in this world. Right. So if you have two different people try to predict the probability of some marketing or some market risk, right? They probably have different opinions. But it's very common. This is this is the most common case in our real life. Right? It's not all the events, all the these parameters can be just very clearly identified, clearly analyzed. So we update the believed probability in their life through all of their life experience. Okay, and this is a very crucial rule for scientists to find and apply to for machine learning. Okay, what machine learning did, what those AI did, those AI stuff, they try to learn the way to update belief in terms of interpretation. They try to use this way to mimic human beings. Okay, later we will talk about one interesting formula that describe in a very easy way to describe this process. Okay, so in this example, okay, for the three occurrence, Okay, which of the following should be most surpriseful? Okay, so definitely where we see, right? If we split the formula 1,000 times, only exactly 3 happens. So in terms of frequency opinion, they may say, okay, you just either repeat the parents for enough time. For the Bayesian's interpretation, just because if after you believe you are not in a certain condition, then it does leave the coin toss to have very low probability for heads. Also, that's also something else. So, what's the frequency interpretation or the Bayesian interpretations of is actually one simple law we can conclude as the law of large number. Okay, so no matter which side you are talking about, whether you believe the frequencies or Bayesians or the type also okay, both of them are actually talking about a simple rule that is the law of large number. That means as far as you observe more observations, the proportion of occurrence for a particular outcome should convert to the probability of that outcome. So in the frequency belief, right, that means the probability is some inherent truth, right? So as we draw the event for the times, right? Exact of occurrence as closer to the probability truth. Bayesian precision, plus repeat it for enough times, okay, you keep updating your belief, okay, the belief will be more comprehensive and not enough sample size. Although the probability may not be a fixed number, as long as you update your probability, it's larger and larger sample size, you will be more and more confident that this probability might apply to different circumstances. Right. But one small thing that we want to mention is that there is one fallacy called the Gambler's fallacy that mistakenly use the law of large number as the law of averages. We can describe this fallacy in this very simple example, right? So if you already flip a coin for 10 times and you get 10 heads, which is very rare, but it's true, you already have this in the past. And now if we ask you to guess the probability of having a tail or having a head in the next toss, you can guess a number larger, lower, or equal to 0.5. Right. I guess as long as you have enough knowledge from the high school, you know that this the answer for this question should be exactly 0.5 because what happens in the past does not determine what happens in the future. So although we describe the probability as a general rule, as maybe a general truth, maybe a good belief for all kinds of events, that does not mean all the results, all the outcomes in the past will aggregate and largely affect so or we call it the whole is not a view for it. Okay. So this one we sometimes call it law of averages. So it means if the average is 50-50, always like the result should convert to the average. The result should not be too much difference from the averages. Okay. It's sometimes also called the gambler's fallacy because very commonly gamblers have these kind of mistakes when they play in the casino, right? So in the casino, the easiest game is to guess big and small, right? You will throw two dice. Okay, if the two dice number is larger than 6, 7, 8, or even 12, then you will have then the result is big. If it's just like 2 to 6, you will have the result is small. So you will see that very likely, although it's wrong, many of the gamblers try to roam around those tables, see which table just have several small in a row or just have several big in a row. And you will see that if one table just have 5 or even more big in a row, many of the gamblers crowd into that table and the back are small. That are your right? They think about, okay, you already have 5B, that's not too small. This should not be true as long as the game is fair. Okay, so we call these examples as this is the misuse of law of large number. Okay, so the law of large number actually describing general opacity. Okay, so like one event should have some kind of probability that lead to in an ideal cases, in an ideal environment, this probability should be true. But in practice, right, our world is full of randomness with a small number of practice, whether the result of as close to the probability or run far away from the probability, that's lots of them. So yeah, so we define some terminologies as still not really hard. Okay, so the first is disjoint. Okay, we in previous version of text tools is a more text tool we call it mutually exclusive. So that means if you have two events, we describe a relationship of two events as disjoint. If these two events will never happen at the same time. So you cannot really pass and fail at the same time for the same class. You will only have one set and those statements. But for two different classes, you can get two grades for both classes. Because this get two scores, two grades. These two have more conflicts. These two events they are given can easily happen together. So we define joint, destroy, and undestroyed. So we mentioned this because you want to recall some of your actual knowledge, like how to calculate joint probability or the unit of events. Okay, so if two events have overlap, all of them together, we call this unit. Okay, if two events are overlap, well, both of them happens, call them intersection. So we first talk about the probability for the unit. Okay, so here for this that, okay, the cards. So we have the probability to draw a red card, and we also have the probability to draw jack, which is the tree there. Okay, we have four cases and another is. So for the drawing probability to have either jack or red, okay, the probability should be the summation of having jack or having red minus jack and red, because here you have an overlap that you can have these two cards that are both a red card and a jack. So to get rid of double counting, okay, we sum the single probability for each event minus their intersection. intersection. Okay, to have a probability for you. So similarly, we can use this example. So if we survey some students about the two questions, one is whether they think marijuana would be legalized. Some kind of medication. Okay, so after two questions, one is whether you agree to legalize marijuana, while the other one is whether you agree to your parents' politics. So we can draw a contingency table like this, like what we have in the slides. Okay, and if here we want to determine the probability for union, that is for double yes. Okay. Right, not really double yes, but one at least one yes. Okay. We want to know that the probability for that the students think that marijuana should be legalized or agree with their parents' critical views. Okay, we know that the students who agree for the marijuana legalization, they are on the second, they are on the second row, okay, 36, 36, the 78, the total 4, okay. They are the total, these are total number of students that agree for the legalization. Then in the second column, this 118, total 118 persons are the total students that agree on their parents' politics. Well, but if we just sum the one together as a total number of students who have at least one yes for these two questions, we actually double count the 78 here. Okay, because it's 78 agree on both sides. And if we sum 118, we actually double count 78. So to get rid of the 78, this double counting issue, we minus this intersection and divide it by the total number of students, so that we can have the correct number for the probability for the unit. Okay. So the conclusion is this general addition rule. Once you want to calculate the probability for a unit, we sum the probability for each single event and take out the intersection. So this now we can link back to the destroy the events we have mentioned before. Okay, because this destroy the event now can simplify our calculation a little bit because it makes the intersection probability at 0. So your bar formula is simplified to PA of B is equal to PA plus. Proceed, this one. So as long as we define the probability for single events, we can also do some similar work for all events and combine all possible events, all possible outcomes together as the so-called probability distribution. Okay, so the probability distribution here, as long as you can define distinctive outcomes one by one, A, B, C, and D. That means that each pair of them are mutually exclusive. Okay, you can actually cover the all possible outcome one by one for one experiment, one events. Okay, so definitely each of the probability of each events should follow the rule like the probability should be seen 0 and 1, the summation of the probability must follow 1 so that you cover all possible defining the correct complete random process. Okay, so in other words, when you define a random process, when you're trying to investigate a random process, you are trying to investigate the probability distribution of events of different outcomes. Okay. So a related question here is that if we survey some citizens about their political preference, their citizenship, okay, if we have sample that 52 of them announce that they are Democrats, then is that correct for us to just say the other 48% are Republican? Well, if there are only two political parties and they must choose one from the two, then the A, 48% of Republicans is true. But there are also some possibilities that they can announce for non-affiliation. Okay, that's have no certain participation. In that case, for these search choices, they will definitely reduce the probability for Republican. So A and C and the different circumstances are both true. Then for a single one request question, like the one that we can only choose the best answer, here we can only choose C. We cannot really calculate because both A and C can be possible. Okay. So just follow the probability distribution, and we can define some similar thing on the sample space. Okay. So here sample space is defined based on all possible outcomes because test. Okay. So here the construction of the sample space can be different from the probability distribution. Okay, for example, generally the gender of a kid, of a newborn is random, okay, either male or female. So to have the gender of a newborn, this is just one single process, random process. But if you define your sample as the result of genders for the two kids, then your sample space is constructed like this. Like a couple has two keys, what is sample space of general two keys? Your sample space has 4 outcomes, MF. Okay? So this is different from the probability distribution for one single random process, like having the gender of a key, right? So we'll define the sample space, okay? It is based on your outcome. If your sample space is depending on two key genders, okay, your outcome will have 4 probabilities. So just following this example, we want to define a new concept on the complementary events. Basically, complementary events are also mutually exclusive, but we additionally require that complementary events, two complementary events, will have their probability sum to 1. So I guess you have seen this kind of before. So so if this is a one random process, then if A happens, B will happen because they don't have overlap. And for the remaining parts, other than A, for the complementary of just a very simple high storage. Beautiful. This one. That's which independent. Okay, independent itself, the concept is the most close to random. Okay. So if we formally define independence, it actually refers to that whether A happen or not will not provide any new information to B's status. Okay, this is how we formally define the independence. So A's status won't really provide any new information to B's status. Okay, so independent is actually the physical assumption for the law of large number we just mentioned several pages earlier. Okay, so law of large number can tell you this if you make your sample rolling, like if you just want to test whether a basket of apple is spoiled, they are bad, they're not good to eat. Okay, so if you always take the one just at the top of the basket, whenever you make your sampling, okay, and every time you put it back, you take it out, you take it out, okay, this one's good, you put it back, and then you take it out, still some apple on top of the basket, so all this one's good, you put it back. Okay, if you repeat this kind of sampling with a strong preference on the top of the basket, you actually making another random sampling, and very likely for each time you sample an apple from the basket, okay, the result is correlated because you are sampling in a very small group. Okay, then you as you have a new type of drawing, actually maybe exactly the same sample, right? It's actually making your sampling non-independent. So if you search about the law of large number, you will see some mathematical formula, and the basic assumption for those mathematical formula is that when you try to do your sampling, each draw of your sample observation should be independent from the others. Okay, each time you independently draw one random sample, I will clear your randomly from population. Each time you draw an independent sample, okay, there are no connections. In that case, the law of large number exists. You can find the truth. Okay, so independent in some cases also very honest. Okay, let's take this example here. So if we survey 500 North Carolina residents, ask them whether they think the gun rights is good or bad. Well, across all the citizens we surveyed, 58 of them think it's good. But if we separated the data into different racial groups, we find that for the white group, for the white group, 67% feels the gun rights is good. 28 of black respondents feel the gun rights is good. 64% of the Hispanic respondents feel the gun rights is good. So here, as long as we mentioned two concepts, one is the agreement on gun rights. The other is the racial ethnicity. So here, based on all the data, we can try to guess, right, whether that ownership and the racial ethnicity in some kinds connected, some kind of relationship. Okay, so as long as you have whichever ethnicity you have, although I don't know why they don't mention Asian, but as long as based on all the three ethnicities you have collected, whichever race you are in, whichever racial group you are in, you have a certain percentage of people agree on dialects. So it seems like they should not be complementary. Right? Complementary means first they need to be mutually inclusive. Second, right, have a certain race and have an agreement on ownership to as a probability equals to one. It seems not all, right? And they are not mutually inclusive, they are not disjoint, and of course they are not complementary. So the question here centers on C and D, whether they are independent or dependent. We can have a rule to check the independence like this. Okay. In general, if two events are independent, that means one event happening will not bring any new information to the other events. So if you build a concept called the conditional probability, use use a column here, also PA on B, we just call it PA on B, okay? So on B is a PSB condition. So we define this as PA on B conditional probability as assuming the B is true, even B is true, B already happens. Under this case, what is the probability of A? Okay, so if these two A and B are independent, then B is happening should not bring any new information to A, so it should have no impact on A's probability. So the conditional probability should be equal to this unconditional probability. So we should have some equation like this. If A will so here we have two things, right? Protect the citizens and the race of the city. Okay? So if we say that B is the race, and A is agree or not, discuss you agree. Okay, agree correct. Okay, B race. So in the previous survey, we already reported the unconditional probability for A, 58. And we observe that PA under different B will shows different pattern. Okay, if we say B1 is white, so PA on B1 should be 67%, PA additional on B2 should be 0.2. B3 by observe the data here, you can see that this is different from K, this is different from K, this is also different from K. Even across the three conditional probability here, they show a significant variation. Okay. Seems like people very unlikely to read the guidelines. So it's this check, you can see that they have some kind of dependence. Different racial group may have different on the guidelines. These are different preferences. Okay. So this is basically another way for to explain what we have had in last week. Right? So last week, by the end of Wednesday, we talk about like events and the case study of random distribution, right? The case study for random distribution, what we had also be written in a way like conditional probability, right? If we define A as promotion, or promotion division, B as a gender, male or female. So those ratios we just will be calculated in the case study is how P promotion and male other is the difference. It's the P promotion. Okay. And why we did the simulation, I mean, try to use a totally natural random group assignment to see that if the event totally runs randomly, okay, how the difference between these number looks like, okay, and we also observe an actual data points, okay, which can be drawn into the distribution. You can see that, okay, throughout the simulated distribution, what we observe is actually quite far away from zero. That makes us have some kind of confidence to see that the promotion and A and B should have some limits. Okay, that's it. Okay. So for these drawings, events, we have the addition rule. For independent events, we have the product rule. So if two events are independent, I have a product rule for the intersection. A and B, if both of them are true, okay, and they are independent, the probability should be just PA modified PB. Okay, so for independent, it has one here. Okay, that's zero of them are kind of smart. Okay, different between this one and the complementary. This one is complementary events are all destroyed events. Also, complementary events, the two complementary events added together, the probability added after one. Okay, so complementary events that have two conditions. Sure. So I utilize the complementary events. You can make some calculations like this. Okay. So if for taxons, okay, here is my example. If for taxons, 25%, around 25% of taxons have no health insurance. Okay, then two randomly selected taxons, okay, the probability for both of them are insured is 0.255 to the power of 2. Okay, for 5 of the taxons randomly selected, if none of them has like health insurance, right, the probability should be 0.255 to the power of 5, right? So, and for the complementary events, right, if we want to say, we want to see the probability for all of them are well insured. Okay, then we first need to calculate the complementary events. Okay, 1 minus 0.255. So this is the probability for one single person that is insured. Okay, and you want to the all the 5% are insured. Then you take the power of 5. And if you want to calculate the probability for at least one are insured, right? Then you need to use 1 minus the probability of all insured. Okay, so difference in that. So yeah, similarly, if underwriters are vegetarian, then if you want to calculate the probability for for three underwriters with at least one is vegetarian, okay, still you take the 1 minus 0.2, take the power of 3 and use 1 minus this power term, okay, you get 0.48. So yeah, you can see that it sometimes depends on how you show the data, right? So if you report to the governor, report to the university, say, so for example, if you are a vegetarian, right, this is a good example to let you know how to persuade your boss, right? So the wrong way is to tell the boss, okay, 20% of people are vegetarian, so we need to open a vegetarian content. A good way is to tell your boss, for any stream, for any stream of persons, any stream of the students, there is about 50% probability that at least one of them are vegetarian. This sounds quite a larger number, right? So this is like how you describe the data in a different way. Right? Although you actually describe the same thing, but you can show it in a way that people would prefer to, right? This is a kind of some trick. So conditional probability, we already mentioned it here. Okay. So we have one experiment here. Okay. Still, sometimes I sometimes feel that those market tax you mentioned too much. Euroclass. So anyway, 72 patients. They are affected by cocaine, some kind of bad medicine. Okay, and now they are seeking treatment. So the conventional treatment is pegylizumab. And now they're trying to drag some new treatment like despermine, antidepressant. So they have relapse, no relapse. So relapse basically means bad. Okay, this is no relapse, that means good. Okay, let's take it as a bad versus good. So this continuation table describes that under three treatments, definitely for good experiment, we have the placebo, which is permin, lithium, and placebo. We want to see that under different treatments, whether the patients get better. Okay, so with this table, we can calculate the probability for generally for all any patients relapse, any patient fall into the bad status. Okay, so we can take the 48 here. This is the number. Also, for the joint probability, okay, we can see that for the people use farming and the relapse, okay, so basically the intersection of these two events, okay, we just take it from the contingency table, one cell, that's the intersection term, okay. So we can use the conditional probability here with a good definition, which refers to the probability of the intersection versus the probability of the condition. Okay, so in this example, so conditional on those patients use metformin. Okay, how much percentage of people relapse? Okay, this can be decomposed into two components. Okay, the first component is the intersection for those both relapse and use metformin, and those use. You can see that the conditional probability is usually in many cases it's usually larger than the intersection case, right? Because now, as long as you have a condition, you are actually restricting yourself into a subsection of outcomes, okay? And you are trying to judge the outcome in this subsection. And maybe this outcome in terms of the total outcome of all possible outcomes is quite a small part. In terms of the subsection, this one might be larger. Okay, so this intersection probability for intersection is the single probability for people use that story. Okay, so okay. Some small mass. Okay, some small mass. The checkpoint independence here is derived from the definition of conditional probability. Right. So if as well as you define a conditional probability like this, okay, A and B. So if A and B are independent, we know that they have the product rule. Right, that means the probability for intersection should be the product of two single probability. Right, they cancel it. We have here very simple math, right? Okay, so for conditional probability, sorry. Okay, and still for conditional probabilities, we call the B, the one here, just after the column, we call it condition, but we never indicate causation with conditional probability. We never say that this one must happen first and this one must happen second. Okay, we just take this as a condition as a restricted path. So that means we can easily flip the second. Okay. But definitely, if you flip the sequence of the result will not be the same. Okay, the result will not be the same. You remember this for me. Okay, you just use time versus before. But if you take the conditional probability like this, you want to access people use that these antidepressants. Within all those people relapse. Okay, you do the calculation in this way. Okay. So if we just flip the definition here a little bit, we can have this called the general multiplication rule. So if A and B equals to E A on B, okay, right, B the function. So still the so let's talk about something interesting here. Okay. finish this in 5 minutes. So what I'm just talking, okay, what I'm going to talk in the following 5 minutes will not be your exam. That's will be interesting. Okay, so we just play some math first. Okay, this is the intersection, the probability for intersection, conditional probability, and the probability for the condition. Okay. So as here, A and B have no samples, right? So we can P A and B or P B and A. We are talking about the same thing, right? That means we can just leave these two letters freely. So we can do it in this way, right? We can use instead we can use A as a condition. This also. So if we then connect what on the right hand side, okay, we just because both of them equals to P A and B, right? So we can say P A on B multiply PB equals to PB on A multiply PA. Okay, this part understandable, right? Lots of step. Okay, we move PB to this side. Okay. So just a small mess. This one, okay, definitely will not be in your exam. Don't worry. This is just very interesting. Okay, this one is on the Bayesian rule. So still, we didn't really do anything specific. Okay, we just play a little bit of math to derive this formula. This formula is very important in current society because this is actually the foundation of machine learning, of artificial intelligence, of DeepSeek, of ChatGPT. Okay, so why? Because this one, that's also why the Bayesian inference is very, very popular, very important in our current society. It's not just this kind of a very simple formula describe the natural process of how any animals learn. Okay, so let's make one example. Okay. If we say A is something we are really, really concerned with, for example, A is the severe event, then A is earthquake. Okay, okay, this is definitely one specific event that we do not expect to happen, right? But they do happen some here and there. So as long as you know here, you probably know that we can observe some kind of events, okay, surrounding the happening of earthquake. For example, let's say we know that some animals, like birds, they do have some reaction to the complicated the geographical change, right? They have some sense that happening, the occurrence of earthquake. So we define this events like birds of normal behavior. So in old days, thousands of years ago, when human beings have no languages, right? We don't really know how to predict earthquake, right? But as some animal, we can learn from experience. So what we observe, what we can sense is that first, by use some, bamboo, tissues, even stones. We can record some big events of history. Okay, so we can get a sense of earthquake. Okay, get the probability of earthquake, although it's a very small number. Okay, maybe this is the probability of earthquake. Maybe, for example, for within 100 years. Okay, we can first by record, okay, record the history of this. It's the same process. We can also record, okay, today the birds are so noisy, okay, it's like something abnormal. Okay, we just record it into bamboo. Okay, we can also record this. So how a human being or how generally how an animal learn from experience? How someone with a brain can learn? They find that okay, as long as the unexpected, the very unhappy event happens, we don't know why. As long as this happens, this thing, first of normal behavior also happens. So because we first concern earthquake, okay, we don't know. We never concern about the first of known behavior. Just by some chance, we observe that okay, as we record the earthquake, coincidentally, we also record the bird's normal behavior. So based on our experience, this probability is high. So take this as a kind of a stable probability, right? Those geographical movements, right? It usually have some kind of frequency, right? So this one is relatively stable. This one is relatively stable. How human beings learn that these two events are actually connected? How we know that once we observe the person of normal behavior, we should prepare to defend for earthquake because observe this additional probability. We know that case in previous case because we care about earthquake, taken the earthquake as a condition, it's very likely the first no behavior happens. So with this process inside our mind, although in 1,000 years ago, right, human beings have no math, they don't really know this one. The brain's behavior can be described in math. But we inherently run this thing, okay? And the next time, when further no behavior happens, we know that it's how any animal learns. Okay, why this is connected to AI? Okay, this is the fundamental of AI. Why artificial intelligence, GPT, DeepSeek can give you good answers? They don't know. They don't know what is the question, what is. Okay, what GPT did is they collect a big amount of data. Okay, they collect this, they collect this. Okay, and by the so-called training, they have a predetermined probability for this. So the first set of few users of AI, for example, if you are the first user of GPT, you key in that, okay, I want to travel to France. They give me a travel plan. Okay, because in the data set they have this, they have that. Okay, although not only for A and B, but for millions of words, paragraphs. Okay, then as you key in something similar to A, okay, they have some judgment, like what you key in, your question is similar to A. Okay, so they run this process to give you the answer. Okay, to give you the best answer. And if you notice that every time after the AI completed their response, in the last row there is a small buttons. There is a one or two small button, right? Ask you to give some response after you about whether this reply is good or bad. Okay. So if you click good, okay, the AI will update this. They will increase this a little bit because you say this response is good. So next time they will also put some similar result. But if you click a bad response, okay, they will reduce this because what they learn is that you don't like it. Okay, and then you given this A, you feel this thing is wrong, you feel this probability is wrong. So next time what the output will be some different response. Okay. So don't worry, I'm not in your exam. Just as long as you already learned until here, right? If you don't know this part, it will be a bit tricky, right? So just want to let you know this part is missing here. Okay. So yeah, that's all for today. That's all for today. Don't worry, don't worry. It's not in the exam, okay? It's not in the exam, you just understand and you hear. No, okay, it's not. So yeah, that's all for today. And if you didn't sign your attendance, sign out here. If you have done the stuff, okay, you can leave. All right. Oh, and by the way, this Wednesday we'll have our first lab. Okay, don't forget. And if you don't know where is Slack, where is Slack 001? Okay, go to check the place a little bit. Okay, don't lose your way.